For so long, we've been searching for that technology that transforms the way we live. Flying cars, robot butlers, 3D printed food. These are all overrated. A technology that we will soon have around the world is mass energy storage. This will enable more people to get cleaner energy more consistently. You get your energy from solar panels and it's too cloudy? Not an issue. Your power comes from the big wind farm down south, but the wind just stopped? No biggie. Energy storage will make renewable energy cheaper and more dispatchable, and push us towards an energy future that doesn't depend on burning our world. There are many potentials for energy storage, too many to count. Pump storage, hydrogen fuel cells, flywheels. But we're chemical engineers. We like chemistry. That's where electrochemical batteries come in. Electrochemical batteries have three main components: an anode, a cathode, and an electrolyte. They use incoming electricity to run reactions, and then run the opposite reaction to create electricity from the movement of electrons. We looked at three different battery types for this study: lithium-ion, lead-acid, and sodium-sulfur batteries. Sadly, every new technology has its own negative impacts associated with it. Since we need energy storage to lessen the impact of energy use, we want the storage technologies we utilize to have the fewest negative impacts possible. How is this determined? With an analysis of their overall sustainability. What is sustainability? In short, it's the ability to meet the needs of the present without jeopardizing our ability to meet the needs of the future. There are many ways of measuring sustainability, but one of the most popular methods is by focusing on the three pillars of sustainability. The three pillars of sustainability are environmental, economic, and social. The impacts of each pillar for each battery are evaluated with indicators that we have chosen from the American Institute of Chemical Engineers and Green Chemistry.
The indicators chosen for the environmental pillar were material use, energy consumed, CO2 emissions, other greenhouse gas emissions, water use, land use, recycling efficiency, and temperature required to operate. From evaluating each indicator, it was determined that lead-acid batteries are the most environmentally sustainable and lithium-ion are the least. Lead-acid batteries are the best environmental option because of their low emissions and energy use during acquisition and production. Lithium-ion batteries are the worst environmental option because of their high CO2 emissions, energy consumption, and water use, which primarily comes from the acquisition of lithium and cobalt. The indicators chosen for the economic pillar were levelized cost of energy, the energy storage cost, innovation potential, energy efficiency, and self-discharge rate, the rate at which the batteries naturally lose power. It was determined that lithium-ion batteries are the most economically sustainable, and lead-acid batteries are the least. Lithium-ion batteries are the best economic option because since they are a mature technology, they have low lifetime costs and high potential for innovation. Lead-acid batteries are the worst economic option because of their high lifetime costs and their poor efficiency and discharge rate. The indicators chosen for the social pillar were the health, fire, and reactivity ratings of the internal components, toxic emissions, dependence on foreign countries, and potential employment. It was determined that lead-acid batteries are the most socially sustainable, and sodium-sulfur are the least. Lead-acid batteries are the best social option because of their low reactivity and fire ratings, along with its low reliance on foreign countries. Sodium-sulfur batteries are the worst social option because of their small employment potential, along with very high fire and reactivity ratings that could be detrimental to workers. By weighing each pillar equally, lithium-ion batteries proved to be the most sustainable. However, it is important to note that the overall sustainability of each was pretty close. This means that any large improvements across the pillars might make that battery the most sustainable. So where do we go next? Well, we should keep investing in each of the three types. There are also other electrochemical cells that should be evaluated to make a full analysis. But right now, each battery has a downfall in one major sustainability pillar. Companies might prefer one over the other based on how they weigh the pillars. For example, if they care most about environmental sustainability, they may choose to invest in lead-acid batteries. Innovation in battery and energy storage technologies is an important step to address climate change and put us on a more sustainable path. a future run by clean energy.